all of you to this post-lunch session, the afternoon session of this program, this course. Now I will briefly tell you about the compressibility. Now compressibility is very important parameter of the fluid mechanics, since we often use the term incompressible flow and compressible flow. So therefore, compressibility is very important to know. So this important thing, compressibility, if we write this compressibility, we will discuss now. What is it? By compressibility of any substance, we mean or we feel a measure of change in volume under the action of external forces. For fluid, this external force is the normal compressive force. As I already told that fluid cannot sustain tensile force, it can only support the compressive force. Now for a quiescent fluid or fluid at rest, the compressive force per unit area, that is the compressive stress, is known as hydrostatic pressure. The details of this thing will be told afterward in the fluid statics part of this program by Professor Sandeepan Ghoshmalli. So if we consider this compressive stress as the hydrostatic pressure for fluid at rest, then we can understand this way that the compressibility of a fluid is defined as a measure of its change in volume under the action of compressive stress or the pressure. Change in volume with respect to pressure. Now, in this regard, a property is defined known as bulk modulus of elasticity, bulk modulus of elasticity is defined like this: minus del P divided by del V by V, where limit of this, I will explain everything, del V tends to 0 or delta V dash. Now let me explain what is that. Delta P is the change in pressure, delta V is the change in volume. Let us make a cut to distinguish it from the nomenclature velocity, and this V cut is the original volume. This is the way bulk modulus of elasticity is defined, and limiting value of this when delta V, this is defined at a point where the delta V tends to 0. But today in the first step I told that exact 0 approaching cannot be done because it will violate the continuum hypothesis. So that means it will approach to, sometimes it is written in many books, in our book also, to a small volume delta V dash, which does not violate the continuum approach. That means this should be very small but large enough to contain a large number of molecules to avoid the molecular uncertainty in predicting the gross behavior of the fluid from statistical average of the molecular behavior. So therefore this will be tending to delta V dash, very small quantity, but from mathematical sense many places it is written as if delta V tends to 0. Now this is the definition of bulk modulus of elasticity. Now one thing everybody understands, that if a substance for which a large pressure is required to change a small volume, this is almost incompressible. The other way, if for a substance, fluid for example, here fluid, we require a very small pressure for which the change in volume is substantial, then it is more compressible. Now let us see from here. Before that we do another thing, this minus sign. Yes, minus sign is here. This is because for all substances in nature, the change in delta P and delta V are opposite in sign for a given mass. That means if there is an increase in pressure, there has to be a decrease in the volume. So therefore a minus sign is deliberately used to define this bulk modulus of elasticity, a property, as a positive quantity. Now for a constant mass, we know rho into V is constant. That constant means the constant mass. So therefore, from this one can write that delta rho by rho is minus delta V by V. That V is again with a cut to define, to distinguish it from the nomenclature V, which is usually given for velocity. So if we put that, then E can be defined in terms of the density like this, delta P divided by delta rho by rho. The minus sign will take care of that, it will be not there, and delta rho tends to 0. Better you write is 0 for mathematical sense, but with the concept that it cannot be 0, it will represent a delta rho for that small volume which does not violate the continuum approach, but for mathematical sense I write this way. So this can be written in differential notation as rho into dP by d rho. Alright? So from both these equations it is clear that the value of E will signify the amount of compressibility or the degree of compressibility, that is the change in volume or density of a substance, fluid. For example, a large value of E for fluid whose value is very large, E is very large, require a large change in pressure to have a given change in density. Or for a given change in pressure, it will be having a very small change in density. Therefore, a large value of E for materials or fluid whose value of E is very large will be almost incompressible. Compressibility is very low. The vice versa also true, that if the value of E is small, then for a given change in the density you require a very small force, or for a small change in pressure, for a given change in pressure your change in density will be substantial because of small value of E. So therefore, the value of E determines the degree of compressibility. For an example, I tell you E for water. We know that liquids are almost incompressible. Why? Because its bulk modulus of elasticity is very large. For an example, the water, the bulk modulus of elasticity is something 2 into 10 to the power 6. Exact value I don't know. It is approximately equal to, is mostly equal to that kilonewton per meter square, because this value d rho by rho dimensionally cancel each other. So the unit of E is the unit of dP. Okay? So by definition, the unit of bulk modulus of elasticity is the unit of pressure. And E for air, common gas which are in use for almost all purposes, water and air. I am giving an example. At 1 atmospheric pressure, now the value of E for gas depends upon its initial pressure, and for air the value of E for 1 atmospheric pressure is the pressure itself. Probably you know the isothermal, I am not going into that detail now. The isothermal compressibility of any ideal gas is equal to its pressure itself. So this is E. There is another compressibility for gas, isentropic compressibility, which is this times the gamma ratio of specific heats, but here it is not that important. The order will be almost the same. That means the modulus of elasticity is 101 for air, for water. So you see, water is almost incompressible as compared to air. Now the question comes that this is the property of the substance. A substance with high E is less compressible. But if I put enormous delta P, enormous change in pressure, that will have a substantial density change. Similarly, gas is, what happened? Similarly, what happened? Huh? Not coming. Should I repeat it or what? Now it is coming. You have seen this thing. All of you have seen this thing. Okay. Now similarly, we can think that for gas, for example air, the E is very low. That means a small change in pressure will cause a substantial change in density. But if the pressure is extremely small, that can utilize the value of E, so the density change may not be there. So therefore the question comes that what is the counterweighing effect between this delta P and the property E. That comes into consideration now for incompressible and compressible flow. Now we know the substance by its inherent property is compressible or incompressible, that depends upon its value of B. But what should be the change in its volume or density, that depends upon our delta P, that change in pressure. So now to fix that, for our practice in fluid flow, we define two paradigm of flow. One is incompressible flow, another is compressible flow. Incompressible flow and compressible flow. And compressible flow. Okay? Now, from common sense, we can understand that we deal with this quantity, the change in volume or density. That means change in density as a percentage or fraction of the initial density. It is known as relative change in density. Whether it is very high or very low, with respect to what? That depends upon the pressure, delta P. How can I tell? With respect to a change in pressure that is brought about by a particular flow. Okay, that is brought about by a particular flow. Now it is the race between these two, delta P and E. How? Because you see now from this expression that from here you see E is equal to rho dP by d rho. That means if you consider del rho by rho, it is nothing but delta P by E from here. So therefore I can write del rho by rho is delta P by E. Now this gives the final picture for our understanding, that if delta P is very high, that you see the counterweighing between these two. Now there may be different combinations. One combination is delta P is very high and E is also very high. Sorry, delta P is very low, E is very high. That means there will be absolutely no change in delta rho. Delta rho by rho is very, very small. There may be a combination, delta P is very high, E is very high. Very difficult to tell what is delta rho by rho. Both are high. I am not conclusive. Similarly, delta P is very low, E is very low, not conclusive. But delta P is very low, E is very high, I am conclusive. That means this will be almost nil. Delta P is very high, E is very low, tremendous change, substantial change. So depending upon the combination, the value of delta rho by rho will be determined. Now let us consider what should be the delta P brought about by flow in a particular situation. Now to know this thing, we have to consider one particular statement, analytical statement, that in any flow, the change in the pressure in the direction of the flow, streamwise direction, is by order of magnitude proportional to half of rho v square. This is a thumb rule that probably all of you know. If you know the Bernoulli's equation also, that means the change in pressure brought about by the change in flow by its change in velocity is equal or proportional to the magnitude of half rho v square. This is known as dynamic head. So change in pressure we can substitute proportionately by half rho v square. So therefore delta rho by rho can be written approximately, because here we are interested in some order of magnitude analysis. What should be roughly the value of the relative change in the density? So therefore we are not bothered about the exact equality, but we can write this is in the order of rho v square by E. Now you see this delta P brought about by the flow is related to the flow velocity. Now when it is done, then we can write one step, that half v square divided by E by rho. And you know that the velocity of sound or the acoustic speed in a fluid medium is given by E by rho. which is known as Laplace's formula, Laplace's equation. So therefore, this will be equal to half v square by a square. That means the speed of sound in a fluid medium depends upon its property bulk modulus of elasticity. That means the nature of its compressibility and the density, E by rho, in this fashion. So therefore, we see that relative change in density equals to half of v square by a square. Now this parameter v by a in a fluid flow, now this parameter, so therefore we come to this delta rho by rho is half v square by a square, with the nomenclature is v is the flow velocity and a is the velocity of sound, acoustic velocity in that medium. Now this ratio v by a, velocity of flow and the velocity of sound, is known as Mach number. Now one thing, very careful, I have also not told correctly that it is the velocity of sound with relative to the flow velocity in that medium. Please note it, it is very important. That is given by root over E by rho, and this v by a ratio is known as Mach number. Mach number. This is known as Mach number. With this nomenclature, this is written as half Mach number square. Up to this, a mathematical analysis, that is delta rho by rho, is approximately proportional to this. Now take an engineering approximation. Delta rho will always change. No matter is there which is 100% incompressible with a value of E infinity. So therefore, always compressibility will be there. There will be a change. Similarly, del rho can never become 0. But from an engineering approximation, if we tell that if delta rho by rho is less than 5%, I ignore that change of density in the flow brought about by the change in pressure because of the flow or in course of flow. Then I can write the flow to be incompressible, flow to be incompressible, flow to be incompressible, therefore flow to be incompressible, what? Half ma square is less than is equal to 0.05, which tells that Mach number is less than is equal to 0.33. It is very important conclusion that it is not the velocity of flow, because the compressibility, how much the density or volume will change, depends upon how much is the change in pressure, and vis-a-vis what it is property, bulk modulus of elasticity, which dictates the change in volume or density because of a change in pressure. So the combined effect of that is determined one side by the flow velocity, which brings about the change in pressure, another side by the bulk modulus of elasticity, which is implicitly expressed through the acoustic velocity. Okay, so therefore it is the ratio that is judged as a criteria whether the flow will be incompressible or not. That means whether del rho by rho will be less than 0.05, when we will consider the variation to be negligible and flow to be incompressible. Now it is obvious the bulk modulus of elasticity for liquid is very high. For water, I have shown that it is 2 into 10 to the power 6 kilonewton per meter square. So therefore velocity of sound is very large, so that a very large velocity is required to make the Mach number more than 0.33 to make water incompressible. If you write the velocity of water through sound through water, it will be so large, and multiplied with 0.33, that large velocity is never encountered in practice. That's why we consider, it is a thumb rule, that flow of all liquids, don't tell incompressible fluid, all fluids are compressible. So flow of liquids with high degree of incompressibility is always incompressible flow. But for gases it is not so, because if the Mach number is less than 0.33, in that case what happens? The delta V associated with that flow velocity relative to sound velocity cannot make that substantial change of density more than 5%. So just give you an example as a thumb rule. For air, our sound velocity, velocity of sound at normal condition is roughly, again I am telling this because I am not very sure, some 335 meter per second. It is close to that, either 336 or 334 like that. So if you multiply that, then Mach number, so V you get 335 into 0.33, something like so. Therefore, as a thumb rule, we say or we calculate, determine in a flow of air, oh, velocity is less than 100 meter per second, it is incompressible flow. Disregard the change in density and go for all calculations of incompressible flow. So therefore, this is precisely the concept of compressibility as a property of the fluid, and how the density variation becomes substantial or not because of the change in pressure brought about by the fluid, brought about by the flow, which brings the concept of incompressible and compressible flow. And we find that when Mach number, that is the ratio of flow velocity to the velocity of sound or acoustic velocity in that medium at that state relative to the medium itself, that means relative to the flow of this medium. It's very particular about that. When this Mach number is less than equal to 0.33. At 0.33, the variation is 5%. And as a thumb rule for air at our standard conditions, normal atmospheric pressure and temperature, 100 meter per second is the borderline, below which the flow is incompressible, above which flow is compressible, and for liquid the value of A is so high, and multiplying with even 0.33 it becomes so high. We never encounter this in practice. Therefore, flow of all liquids, it is not for water, water is an example, all liquids, the flow of liquids is incompressible flow. Thank you. This is our revisit to the concept of compressibility, compressible and incompressible flow distinction. Now, I invite Professor Sandeepan Ghosh Mollik. Oh, sorry, there will be tutorial classes. So, I think the introductory concepts we have been able to finish. I started with the definition between, distinction between definition of fluid with special emphasis on the distinction between solid and fluid, then the concept of continuum, then Professor Suman Chakraborty emphasized on 3 points. How do you characterize the stress, how the stress is defined on a fluid element, how can it be characterized, how can it be represented, then the concept of viscosity is very important concept, and then the concept of surface tension is also another important concept, and finally the compressibility and incompressibility, incompressible and compressible flow idea and concept. This closes the section or chapter of introduction to fluid flow. Now I request my teaching assistants to go for some tutorial classes so the concept will be made more clear. Thank you.